Hello friends, good afternoon and welcome to EduSite Live Lectures. Dear friends, today we are going to talk about isomerism. To discuss this topic, we have with us our subject expert, Dr. Aparajita Chauhan. Dr. Chauhan is Associate Professor in Department of Chemistry in Sri Aurobindo College, University of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you. Hello viewers, today we will be discussing isomerism, and along with isomerism I would take little bit of basic organic chemistry. So when we talk of isomers, what are isomers? Isomers are compounds which have the same molecular formula but they have different physical and chemical properties. Why do they have different physical and chemical properties? It is because of difference in their structures. Now when we say difference in their structures, what type of difference in their structures can they have? First is, that is the molecular formula is same, but the arrangement of atoms in molecule is different. That is, the bonding sequence is different. Second type of isomerism is stereoisomerism, in which the molecular formula is same, structural formula is same, but the arrangement of atoms in molecule in space is different. So this is what is isomerism. Because of the difference in arrangement of atoms, the molecules end up with different properties. The term isomerism was given by Berzelius, and its Greek meaning, it has been derived from a Greek word in which iso means same and meros means part, and it describes the relationship between molecular arrangements that, although differing in chemical or physical properties, have a level of commonality. That is, they have same parts. Now, before I proceed further with isomerism, I would like to go back to the origin of organic compounds. Initially, it was believed that organic compounds are synthesized in nature under the influence of some mysterious force, which was on basis of which Berzelius gave vital force theory. And initially, Scheele isolated some molecules from organic molecules from animal and vegetable sources. Later on, and they said that these were prepared in nature under some mysterious force. But later on, when Wohler was heating ammonium cyanate, he ended up with a new compound which was urea. And this compound surprisingly had the same elemental composition as ammonium cyanate, but its properties were entirely different. Its properties resembled those of urea which we isolate from human urine. So how is it that the two compounds which were having the same molecular formula, they had different properties? Maybe it was due to difference in their structures. At the same time, Pasteur, while synthesizing tartaric acid, found that when he separated two types of crystals, that is the left-handed crystals and the right-handed crystals, they had different effect on the direction of rotation of plane polarized light. So that means these compounds they have the same molecular formula yet different properties. So this gave rise to the concept of isomerism, and concept of isomerism is central to structural chemistry. This concept has been beautifully encapsulated in the title of the book by laureate Hoffman, Same and Not the Same. That means the molecular formula is same, yet the properties are different. If we look into this slide, what it shows, many things in nature look similar, but they are completely different. Here we have two species. What we find is that they have very similarity, like similarity in hairs, eyes, expression, balding of hair, yet since they belong to two different species, their properties are entirely different. So we can say that they dance differently to the same music. Now the question arises, are isomers homologues? Then they are known. Let's revise what we've done in our earlier lectures. Homologues belong to the same family having same functional group. And the difference between the two consecutive members is CH2 unit. That means the molecular formula is different. Whereas what we've discussed till now is that isomers have the same molecular formula. Secondly, when we talk of homologues, homologues show gradation in their physical properties and they have similar chemical properties. The chemical properties, the order of reactivity may be different. Whereas in case of isomers, the physical and or chemical properties may be different. So we can say it in a very simple language or in layman's language, then homologues dance similar to the same music, whereas isomers dance differently to the same music. That isomers, in spite of having same molecular formula, will show different properties. Now, what type of isomerism can we have? When we talk of isomerism, isomerism can be broadly classified into two forms, structural isomerism and stereoisomerism. Structural isomerism comprises of chain isomerism, position isomerism, metamerism, tautomerism, and functional group isomerism. Stereoisomerism is of two types, conformational and configurational, and then we can further divide configurational into geometrical and optical isomerism. In today's lecture, we will be discussing chain and position isomerism in details. Now, when we talk of chain isomerism, before I proceed on to chain isomerism, I would like to discuss the property of catenation of carbon. Carbon has the unique property of catenation. That is, it has a unique property of self-linking to form straight chains, branched and cyclic structures. This may give rise to chain isomerism, that is the carbon skeleton is different, or ring chain isomerism. So when we talk of chain isomerism, it is because of the unique property of carbon, that is of self-linking, because carbon can form strong bonds between its cells as well as with other atoms like oxygen, hydrogen, nitrogen and sulfur. So what we find is that because of this property, we can have different structures. So before we go on to isomerism, I would like to discuss the structure of alkanes. So what is chain isomerism? In chain isomerism, the compounds have same molecular formula but different structural formula. That means the carbon skeleton is different. So now if we look into the simplest hydrocarbon, that is methane, then it has only one carbon and only one structure is possible. And this carbon is primary carbon. If I go on to ethane, then ethane again has just two carbons, and because of these two carbons, only one structure is again possible. And these two carbons are again primary. So when I go on to next homologue, what we can do is we will replace one hydrogen with a methyl group. So when we do this, in this case also both the carbons are primary. Therefore, what we find is we have propane. And now we can write different structures for propane. Before I proceed further, how do we decide the given compounds are isomers or not? We have to look into the structure of the molecule. If the structure is same, then we say they are not isomers. If the structure is different, then we say they are isomers. So in case of propane, what we find is that we can write different structures for propane. In first, the one methyl carbon is bending upwards. In the second, it is twisted downwards. Then we have it again twisted up. But all the structures what we observe is that the longest carbon chain has 3 carbons in it. So that means they are not isomers. They are simple structures of propane because of the free rotation about carbon-carbon single bond or carbon-carbon sigma bond. Now if we look into propane, then what we find is propane has 2 types of carbons. One is primary carbon and the other is secondary carbon. Now I have an option here that I can replace this hydrogen, that is a secondary carbon, with a methyl group, Or we could have replaced a primary carbon hydrogen with a methyl group ending in two different structures. If I replace one hydrogen, that is the primary hydrogen, I get N-butane. Now when we write the different structures for N-butane, what do we find? Again, we can write branch structures for this, but all the structures are similar. So this isomer is normal butane. In second case, what we have is we've replaced a secondary hydrogen of the propyl group, and what I am getting here is isopropane. But when I write the structures for isopropane, again all the structures are similar. So we come to the conclusion that butane has only two isomers, chain isomers, that is normal butane and isobutane. Now let us look into pentane. So when we look into pentane, what we find is, we go back to butane. And when I talk of butane, normal butanes has two types of carbons, the primary carbon and the secondary carbon. In this case, if I replace a primary hydrogen with a methyl group, I get normal butane. And if I replace a secondary hydrogen, then we get a isobutane. Whereas in case of isopentane, when I talk of isobutane, then in that case again two possibilities are there. First is that we replace one hydrogen with a methyl group when we'll get a neopentane. So when we look into the bond structures, then what we find is that pentane can give rise to two isomers. One is normal pentane and the second is isopentane, but in this structure, since both the methyl groups are at the second position, so we say this is not an isomer. So normal pentane is giving rise to two isomers, that is isopentane, isopentane and secondary pentane. If we talk of the next structure, which is isobutane, that will give rise to isopentane, and then this can have isopentane. We can replace two hydrogens, one from the tertiary carbon. When we do that, we are getting neopentane, and when we remove a hydrogen from a primary carbon, what we are getting here is isopentane. Now what we find is that as the number of carbon atoms are increasing, the structural isomers are increasing. That is, for methane, ethane and propane, we just have one structure. But for butane, we have two structures. For pentane, we have three structures. Hexane, 5 structures. And if we talk of C30, we have something like theoretically billion structures of this molecule are possible. And for C40, we have something like trillion possible isomers. So these are very large in number. So now next what we go on to is what will happen to their properties. What we find is that as the branching increases, the boiling point decreases. Why is this so? Because when the branching decreases, the surface area in contact becomes less. And since the surface area in contact is less, the van der Waals forces are less, because of which the boiling point is low. Similarly, melting point is also low. If we talk of the melting point, that is also low because with branching, because then the symmetry is less, packing efficiency is less. And for a straight chain hydrocarbon, what we find is that they are more. So if we look into hexane molecule, what we find is similar thing, that with branching, the boiling point, the melting point and the density are decreasing. Whereas if we look into the solubility of the molecule, then the solubility increases with branching because the van der Waals forces become weak and the surface area in contact is also less. So that means chain isomers have different physical properties. What about their chemical properties? Will the chemical properties be also same or they will be different? They will be same because they belong to the same homologous series. Only what is different is the functional group is not different here. So they will show similar chemical properties. The only difference here is that the order of reactivity may be different. That is, if I am talking of alkanes, then we know that alkanes undergo free radical substitution reactions. So here what we can say is that since the tertiary free radical is most stable, the order of reactivity of towards halogenation or any other free radical substitution reaction for alkanes would be that tertiary hydrogen will be most reactive, secondary will be less, primary will be least. That means that a secondary butyl chloride will be formed more readily as compared to isobutyl chloride. So this is what we mean here, that is, but the chemical properties will be same, that in both the cases we will get halogens. Now if we look into, I've shown you some more compounds which are showing chain isomerism, that is N-butyl alcohol is isomeric with isobutyl alcohol. Here the chain is different. N-butyl chloride has 4 carbons in the straight chain, whereas isobutyl chloride has 3 carbons in the straight chain. Similarly, in butyric acid, normal butyric acid has 4 carbons in the straight chain, whereas in isobutyric, we have a methyl group at the second last carbon. Not only this, 1-butene and 2-methylpropene are also chain isomers, because in normal butene we have 4 carbons in the straight chain, whereas in 2-methylpropene there are 3 carbons in the straight chain and 1 is occurring as a substituent. Now in this case again, if I talk of 1-butene and 2-butene, then what we'll find is that 2-butene is more reactive towards electrophilic addition reactions as compared to 1-butene, but the reaction will be same, that is both will react with HBr, if we talk of HBr, to give us butyl bromides. The second class of isomerism that we come across is position isomerism. What is position isomerism? In position isomerism, the carbon skeleton is different, is same, but the position of the functional group is different. That is, the functional group is also same, but its position is different. That is, it may occur at one position or position number 2. So for example, if I talk of butane, then we know from butane that we have 2 isomers, chain isomers for butane, that is normal butane and isobutane. And now if I talk of normal butane, I can remove a hydrogen from the primary carbon, which will give rise to a normal butyl group. And whereas if I remove a hydrogen from a secondary carbon, it will give rise to a secondary butyl group. So now if I replace this with any of other functional groups like a halogen or an alcoholic, what we will get here are 2 position isomers. Whereas if I look into isobutane, again here we have 2 possibilities. One is we can replace a primary hydrogen here with a halogen, in which case we will get a isobutyl, whereas in the tertiary butyl again we will get a halogen here. Here the position of the atom, the halogen, the functional group is different. So what we say in both the cases, the carbon skeleton is same, that is for butane, but we have 1 chlorobutane and we can have 2 chlorobutane, that is the position is different. Let us discuss this further while taking the example of pentane. We have already discussed that pentane has 3 isomers, normal pentane, isopentane and neopentane. Now if we look into normal pentane, then C1 and C5 are similar. That is what I mean here is that if I replace a hydrogen at C1 or C5, we will get the same isomer, whereas C2 and C4 are similar, that is C2 here and C4 are similar. So if we replace hydrogen here with a halogen, we will get a similar isomer. So in this case, we can get 3 isomers, position isomers, that is 1 chloropentane, 2 chloropentane and 3 chloropentane. Now if we look into isopentane, then what we find in isopentane is that number 1, carbon number 1 and number 5 are similar, whereas C1, C2, C3 and C4 are different. So that means we will get 4 position isomers in this. 1 chloro 2 methyl, 2 chloro 2 methyl, 2 chloro 3 methyl butane and 4 chloro 1 chloro 3 methyl butane. So what we find is in first case the chlorine is attached to a primary carbon. In second case it is attached to a tertiary alkyl halide. Again third is a secondary alkyl halide, and first one is a primary alkyl halide. The difference between the first and the fourth is that in first it is 1-chloro-2-methyl, whereas in the fourth it is 1-chloro-3-methyl. So here the position is different of the alkyl group. Now the last isomer of pentane is isopentane, and when we do its monochlorination, what we get is neopentyl chloride, because in this case all the carbon atoms, that is C1, C4, C3 and C5, all of them are similar. So we get only one isomer. So when we talk, if the question is asked, how many monochloro derivatives of pentane are possible, then we have 8 isomers for it. That is 3 for normal pentane, 4 for isopentane and 1 for neopentane. Not only the substituents of alkanes, but also what we find is that alkenes and alkynes can also show position isomerism. That is, in them, the position of the double bond is different. Here the functional group is double bond. So what we find here is that in the first example, the double bond is at the second carbon. So this is 2-butene, whereas in this case, the double bond is at first carbon, so it is 1-butene. What we find is, we know that if we talk of benzene, then benzene on mono substitution gives only one product. But if we do di substitution, 3 possible isomers are possible. So what we see here is, the first is the ortho dicarboxylic acid, second is the meta, that is 1,3, and the fourth one is the 1,4 or the ortho dicarboxylic acid. So what we find here is the properties will be different, that is their physical properties will be different, and in some cases their chemical properties may be different. Like in this case, if we are treating this, we heat this acid, that is phthalic acid, or benzene 1,2-dicarboxylic acid, it on heating easily loses water molecule to form phthalic anhydride, whereas terephthalic acid and isophthalic acids do not do so. Now let us take this structure. Do you think these are position isomers? No, they are not position isomers. Here the position of the methyl group is different. That is, in first example it is at the second carbon, whereas in the third it is at the second example it is at the third carbon. But this is just an alkyl group. These are chain isomers, because in this the carbon skeleton is different, the functional groups are not different. So what is the difference between a chain isomer and position isomer? In chain isomers, the carbon skeleton is different, whereas in position isomers, the position of the functional group is different. So now if we look into this structure, what we find is these two structures are position isomers of alkenes, that is, the position of the double bond is different. This is again a position isomer, that is 2-methyl 1-pentene, 2-methyl 2-pentene, 3-methyl 1-pentene. These are position isomers. Now if we look into the third structure, then what we find, if we compare these two structures, then what we find is, if we are comparing the two, then these are the chain isomers. Now if we look into a question before proceeding further, then what we know is that a compound has molecular weight 72, and it on monochlorination gives 4 compounds, isomeric compounds. How would we solve this problem? We will put the general formula for the series alkanes, which is CnH2n plus 2, which is equivalent to 72. Now we will find out n. When we find out n from this formula, we find that the n is 5. That means the isomer is pentane. And I have already discussed in details, that is, that isopentane on monochlorination would give us 4 products. So the compound is isopentane. Now the ball is in your court. You have to look up more examples and solve them yourselves. Thank you. What is functional isomerism? In functional isomerism, two or more compounds have same molecular formula but different functional group. So when we say they have different functional group, that means the physical as well as chemical properties of these compounds would be different. So if we look into aldehydes and ketones, then what we find is that aldehydes and ketones are functional isomers. What is different in them is that is their chemical properties are same, that is they will undergo nucleophilic addition reactions. But what we find here is that aldehyde group is more polar as compared to ketonic group. So this will undergo nucleophilic substitution reactions more readily as compared to propane. And then what we find is that this will also undergo oxidation more readily as compared to a ketone, that is as compared to propanol. Not only this, that aldehydes and ketones are isomeric among themselves, they are also isomeric with unsaturated alcohols, and ketones are isomeric with cyclic ethers. So now when we talk of an unsaturated alcohol, it will show the properties of an alcoholic group, that is it will show us some acidic properties, and it will also show us the properties of double bond, that is it will undergo electrophilic addition reactions. Whereas this molecule will undergo nucleophilic addition reactions. This is also more polar as compared to a double bond here. If we look into ethers, then ethers are chemically inert and they act as solvents. Whereas when we talk of ketone here, again it will undergo nucleophilic addition reactions and some reactions due to presence of alpha hydrogen also. What the other class of compounds which we found are functional isomers are alkenes, cycloalkanes, and alkenes and cycloalkanes have the same general formula, that is CnH2n. So in case of butene, that is alkene, the reaction will be electrophilic addition reactions, whereas cycloalkane, because it's a 4-membered ring, so it is quite reactive, so it may undergo addition reactions as well as substitution reactions. So when we look into these two structures, then what we find here is that structure number 1 and the 2, that is what these are the position isomers. If we compare these to the next here, then these are chain isomers. And if I compare this with the third structure, then this is a functional isomer of pentene. So what we know here is that if the molecule is complex, the molecular formula is complex, then it can exhibit more than one type of isomerism. That is, this molecule is exhibiting position isomerism, then this is exhibiting position in itself, but when we compare these two, these are chain isomers, And when, that means these are structural alkenes, these are isomers of pentene. And then when we can compare it to another structure which is cyclopentane, and this is showing ring chain isomerism. This is because of the unique property of carbon, that is, it can form straight chain as well as branched structures. Now if we look into next slide, then here I have discussed more examples of functional isomerism. What we know is that alcohols and ethers are functional groups. They have the same general formula, and in alcohols the functional group is OH, whereas in ether the functional group is O. They have the same molecular formula, that is C2H6O. They have two different structures, and because of these two different structures the chemical properties are different. That is, alcohols have higher boiling point because of intermolecular hydrogen bonding, and they are also soluble in water, whereas ethers are not soluble in water because they are incapable, they do not form hydrogen bonding. Next, what we look here is, if I look into alkynes and alkadienes, then alkynes and alkadienes are also functional isomers, the general formula being CnH2n-2, and but here again the properties would be different. That is, butane will undergo electrophilic addition reaction, whereas butadiene will also undergo electrophilic addition reaction. But butadiene will be more reactive as compared to butane. And secondly, alkynes can also undergo nucleophilic addition reactions. Next, if we talk of next class of compounds which can act as functional isomers are acids and esters. Acids are acidic because of the presence of hydrogen which is attached to an electron withdrawing group, whereas esters are not acidic. They are less reactive as compared to carboxylic acids. And esters on hydrolysis will give us back acids, whereas these compounds, the other class of compounds which is isomeric with them is 2-hydroxypropanol. This is entirely a different compound, and this will show us the properties of the aldehyde group as well as the alcoholic group. See, one can go back to an acid and say here also we have a carbonyl group and a hydroxyl group. Why does it not show properties similar to an aldehyde or a hydroxyl group? It does not do so because of the presence of resonance here. So it undergoes nucleophilic substitution reactions here. Whereas what we find in this case is that this will undergo nucleophilic addition reactions, and here again we will have nucleophilic substitution reactions. But here the acids are more acidic than alcohols. So this is the difference in their properties. And the next class of compounds are hydroxyalkanols. Again, they will show similar properties, that is, they will show the property of an ketonic group as well as the property of an hydroxyl group. The next class of functional isomers are nitriles and isonitriles. Again, what we find here is the molecular formula is the same, but their properties are different. For example, if we do hydrolysis of cyanide, then we will get an acid having same number of carbon atoms. That is, in this case, I will get ethanoic acid. Whereas if I do the hydrolysis of this compound, then this will behave very differently. That is, we will get a primary amine and formic acid in this case. So the properties are different. Whereas if we do the reduction of a cyanide, we will get a primary amine. And if we do a reduction of a isonitrile, we will get a secondary amine. Similarly, what we find is that nitrites and nitroalkanes are also functional isomers. And when we do reduction of nitrite, we will get an alcohol, whereas when we will do the reduction of a nitro compound, we will get an amine. So what we find here is that compounds are having same molecular formula, but because of the difference in the functional group, they have drastically different chemical properties, and therefore organic compounds are vast in number, and we have versatile options to synthesize many organic compounds. Now, if we go on to next type of isomerism, then that is metamerism. What is metamerism? Metamerism is special type of position isomerism in which the functional group is same, but the alkyl group on either side of functional group is different. That means the functional group interrupts the main carbon skeleton. In this case, functional group has to be divalent or trivalent, like it can be oxygen, it can be an amino group, it can be a ester group. And they belong, the metamers belong to the same homologous series. So if we look into the examples of metamers, then what we find is that methoxypropane and ethoxyethane are metamers. In this case, what we find is that the functional group is same, that is, it is oxygen, but the alkyl group on either side of functional group is different. That is, here it is methyl, whereas in this case it is here propyl. And if I look into the next example, then in both the cases it is ethyl and ethyl. That means methyl is different from ethyl, and again ethyl is different from propyl. So these are metamers. If we look into another example, some more examples, then what we find is methyl acetate and ethyl formate both have the same molecular formula, which is C3H6O2, but they are different. That is, in this case, the ester group is different. The alkyl groups on either side of COO is different. In one case, it is methyl, and in the other case, it is ethyl. If we look into secondary amines, that is C4H11N, then this will again show metamerism, that is the alkyl groups on either side of NH. In one example are methyl, whereas in the second it is ethyl, and then if we compare the second group, then it is propyl in one and ethyl again in the other. So these are examples of metamerism, metamers. Again, what we find is, if we look into the C4H10O, as I said earlier, that one compound can exhibit more than one type of isomerism, then what we find here is that in case of C4H10O, it can have two isomers, that is position isomers, 1-butanol and 2-butanol. And then if we compare it to the next example, then this is a chain isomer of the first, that is 2-methyl-propanol. And then the second is tertiary butanol. So these two are the position isomers, and if we compare them with the first, these are the chain isomers. Now if we look into the next example here, what we find is that these two are chain isomers and these are the position isomers. Now if we look into the next, what we find is these are the functional isomers. That is, in alcohol, the functional group is OH, whereas in case of an ether, the functional group is oxygen. So here the functional group is oxygen, here the functional group is OH. So these are functional isomers. Not only this, what we find is, if we compare the two ethers among themselves, then they are metamers. So now we have variable questions on this formula C4H10O. If the question is asked, how many isomeric alcohols do you have? Then the answer would be 4. Normal butyl alcohol, isobutyl alcohol, secondary butyl alcohol, and tertiary butyl alcohol. If the question is asked, how many functional isomers? Then we will include the isomeric alcohols as well as metamers. So that means the number of isomers would increase. Another set of now if we look into amines. Amines are a very interesting class of compounds, and if I ask you how many structures would C5H13N have, or how many isomers would it have, it would have large number of isomers. Before we proceed further, I would like to clarify one thing here, that till now we have not said that primary alkyl halide or a secondary alkyl halide are functional isomers. They are position isomers, because in that case, the position of the halogen is different. The functional group halogen is same. But if we compare primary amine, secondary amine and tertiary amine, then what we find is these are functional isomers. So in case of amines, the number of isomers increase very much. And not only so, we will get position isomers, we will get chain isomers, we will get metamers and functional isomers. So now if we look into amines, what we have is 17 structures, 17 possible structures are there. That is, in case of a normal amine, pentylamine, then what we find is that again C1 and C5 are equivalent, C2 and C4 are equivalent. So in this case, we are getting 3 position isomers, 1 pentanamine, 2 pentanamine and 3 pentanamine. If we go on to the next one, then here we have chain. So when we talk of isopentane, here again what is possible is 4 isomers are possible. 1 butanamine, 2 methyl 1 butanamine, 2 methyl 2 butanamine, 3 methyl 2 butanamine and 3 methyl 1 butanamine. So these are the position isomers. If we talk of a secondary amine, now this is secondary amine is functional isomer of primary amine. In this case, the functional group is NH, and in this case we will get 6 secondary amines. So the number of isomers have increased. Not only this, what we find is in these secondary amines are functional isomers of primary amines and tertiary amines, and they among themselves are showing metamerism. That is, for example, if we look here, the functional group is NH, but on the one side the group is methyl and on the other side the group is propyl. Here the group is methyl, and in this case the group is ethyl, and here the group is propyl and butyl, and here the group is propyl. So what are these? These are metamers. So all these are examples of metamers. Next we have tertiary amines. In tertiary amines, the functional group is N. So in primary amine, the functional group is NH2. In secondary amine, the functional group is NH, and in tertiary amine, the functional group is N. So that means they are functional isomers. Now, how many tertiary amines are possible? We have 3 tertiary amines, and they can also show tautomerism in case all the alkyl groups they can also show metamerism in case all the alkyl groups attached to nitrogen are different. Now, if we talk of amines, then we can say amines are derivatives of ammonia. In primary amine, the functional group is NH. In secondary, it is NH2. In secondary, it is NH, and in tertiary amine, it is N. So what we've seen is that if the molecular formula becomes complex, the number of isomers will also increase. Now we talk of another type of isomerism, which is tautomerism. Tautomerism is a special type of functional isomerism in which there is dynamic equilibrium between the two forms. That is, one form is readily convertible into the other form. This term was first used by Lahr in order to explain the reaction of a substance according to 2 possible structures. That is, it could give us properties, show us reactions due to the presence of a carbonyl group or due to the presence of an enolic group. And this results in the molecule due to the wandering hydrogen. That is, hydrogen migrates from one atom to the other atom. And since hydrogen is migrating, it is also known as prototropy or desmotropism. Now, tautomerism can be of 2 forms. That is, first is the diet system. Now, when we talk of the diet system, what we find here is that hydrogen migrates from first to second carbon. That is, it is migrating from this carbon to this nitrogen. So this is known as the diet system. We can also have another system which is the triad system, and the common example of this is keto-enol tautomerism, and today we will be discussing in detail keto-enol tautomerism only, whereas other forms of tautomerism are also possible. Now, so when we see here, in this case, the hydrogen migrates from first carbon to the third atom. So what is here? Here this is the triad system, that is migration is from the first to the third. In this case, the functional group is the keto group, whereas in this case, the functional group is the enol form. Not only the proton has migrated, even the double bond has shifted here. That is, here the double bond was between carbon and oxygen, and in this case, the double bond is between carbon and carbon. So this is the enol form. So what is an enol form? Enol is that in which the OH is directly attached to that carbon which is having a double bond. So this system is an enol form. And this is a dynamic system, that is, one form is constantly changing into the other form. So that means if I add a reagent to it which will react with the keto form, then the entire form will behave as though it is made up only of ketone, because as the ketone is used up, more and more of enolic form will be converted to ketonic form, and vice versa. That is, if we add a reagent which will react with enolic form, then the whole system will behave as though it is made up of enol. So that means when I have a keto form, it will give us a positive reactions of aldehydes and ketonic groups. That is, they'll undergo nucleophilic reactions. They will give us reaction with phenyl hydrazine hydrochloride, whereas enolic will give us a violet color with neutral FeCl3. Hence, the chemical properties are different. They are behaving chemically different. So here what we find is, this is what is happening is tautomerism. In this, enol is directly, the OH is directly attached to a carbon which is sp2 hybridized. This is the enolic form, and this form is constantly changing into the aldehydic form. Is this an enol? What do you think? It is not an enol. Why? Because here OH is attached to an sp2 hybridized carbon. That is, it is attached, sp3 hybridized carbon, it is attached to a saturated carbon and not to an sp2 hybridized carbon. That is, it is not attached to directly to a double bond. So this is not enol. It will show us the properties of a double bond and an OH group. These will not affect each other so drastically. So this will not exhibit tautomerism. Now the question arises, which of the two forms, the ketonic form or the enolic form, which is more acidic? The enolic form is more acidic here because the H is attached to a more electronegative atom which is oxygen, whereas here hydrogen is attached to a carbon which is not electronegative. Here the difference in electronegativity of carbon and hydrogen is not that great, where here it is a lot. So we say enolic form is more acidic as compared to the keto form. And because it is more electronegative, therefore the proton can be released more easily. Now, when we talk of tautomerism, can all carbonyl compounds show tautomerism? Then the answer is, that is, for a molecule to show tautomerism, it should have one acidic hydrogen. What do we mean by saying an acidic hydrogen here is that this carbonyl group is an electron withdrawing group. So when it withdraws electrons from here, the bond between this carbon and hydrogen becomes weak. And this is an alpha hydrogen. So since this bond becomes weak, then in presence of a base, this hydrogen can be given off as a proton. So this hydrogen is acidic in nature, and then this hydrogen is acidic in nature and is given off as H+. And what we find is that water catalyzes this reaction. That is, water can act as an acid as well as base. So what we find is that it will help us in conversion of a ketonic group to an enol or to an enol to a ketone. And what we find is this is quite basic, because here the anion which is formed here is resonance stabilized. So for a compound to show tautomerism, it should have an acidic hydrogen, because this is that hydrogen which then migrates to this oxygen and will convert this keto form into enolic form. Will the compounds which we have shown on the slides show tautomerism? What do you think? The first structure, which is benzaldehyde, does not show tautomerism because it does not have alpha hydrogen in it. We have removed this CHO, and since we know this carbon is sp2 hybridized and here it was CH, and we have already replaced the H with a CHO group, so that means this will not show tautomerism. Here we do not have alpha hydrogen. Again, here we do not have alpha hydrogen. All the alpha hydrogens have been replaced with methyl groups. So this compound, that is tertiary butyl phenyl ketone, will also not show tautomerism. If we go on to next structure, benzophenone, again this does not show tautomerism because this does not have alpha hydrogens in it. Benzoquinone, of course, does not, no alpha hydrogen here. And this cyclohexane derivative, in this we have replaced all the alpha hydrogens with methyl groups. So this compound will also not show tautomerism because it does not have alpha hydrogen. So for a compound to show tautomerism, it should have alpha hydrogen in it. Now the question arises, what is the stability of tautomers? Which tautomer is more stable, keto or the enol form? Generally what we find is that the keto form is more stable as compared to enol form, because in keto form the bond strength of CO is more, C double bond O is more as compared to bond strength of C double bond C. So keto form is more stable, and keto form is generally in water. It is 99.9% is acetone and only 0.1% is the enolic form. But this order of stability may change in different solvents and also due to the result of the structures. So if we look into these structures, which is a structure of a diketone, then what we find here is that this diketone, in this case, the enolic form is quite bit, whereas in case of acetone, what we found was that the enolic form was only 1%. Why was it only 1%? Because the keto form was more stable. In this case, the enolic form is 15% because of the formation of intramolecular hydrogen bonding. Intramolecular hydrogen bonding is possible here. So because of that intramolecular hydrogen bonding here, from 0.1% to 15%, for acetone it was just 0.1% of the enolic form, whereas in case of diketone, that is pentane 2,4-dione, the enolic form is 15%. Not only this, what we find in case of phenol, it is exclusively the enolic form which is there. Why? Because the enolic form is aromatic in nature, and we know that aromatic compounds are more stable. So it would not like to undergo tautomerism and convert itself into the keto form, which is less stable. Why is the aromatic form more stable? Because here the pi electron cloud is delocalized over the entire ring, whereas when we talk of the keto form, in that case one of the carbon becomes sp3 hybridized, and because of that change in hybridization the molecule would lose its aromaticity. So we say the exclusive structure for phenolic form is the enolic form. Now the question arises, how does this tautomerism take place? So this we shall be discussing in our next lecture. If you have any queries, you can always get back to me. Thank you.
On that note, I would like to thank ma'am for this very enriching lecture, and I hope, dear friends, that you have enriched and you have got a better idea of what isomerism is all about and what its various manifestations are. And on that note, I would like to thank you, dear friends, as well for watching our show. Stay tuned and keep watching. Thank you.